Hello and welcome to the next video. In this video what we will do is we will step back a little and revise the concepts which we have studied till now, and so that we understand the concepts. In the last few videos we pretty hurriedly went through the concepts in order to derive some things, but now we will in this video we will just concentrate on some of the concepts. So for the photoelectric effect as well as the Bohrs model, if there is something of a catchphrase, or if I want to summarize the basic underlying concept excuse me, the basic underlying concept in one sentence, then that concept would be conservation of energy. Conservation of energy. Okay, so we have derived most of the things using the conservation of energy. Okay, and we'll see how it is. So before that, some basic concept. Light as well as all the photons or any wave which exhibits wave particle duality has an energy. Therefore light has an energy, and that energy is given by the Planck's constant multiplied by mu, h mu, and mu from our basic, mu is the frequency, and from our basic understanding of waves which we covered in class 11th, mu can be written as the velocity divided by the wavelength of the light. Okay, so this is one basic formula. The energy of a photon is given by, or any radiation is equal to h mu. Okay, now the next concept is the photoelectric concept. So if I have a energy or radiation which is hitting the surface, and because that energy transfers its energy to an electron, so electron absorbs this energy, this photon, and it gains energy, and it will be able to overcome the basic nuclear force with which the nucleus is attracting the electron towards it. So to overcome that force, it needs a minimum energy of phi, which is the minimum threshold energy which is required to overcome the nuclear force of attraction. And if this h mu is at least enough or more than phi, then the electron, at least equal to phi or more than phi, then that electron will be ejected, and the kinetic energy of the electron ejected from the conservation of energy. From conservation of energy, hc by lambda is the energy which has been transferred to the electron. Okay, out of that hc by lambda, phi energy has been used to overcome the nuclear force of attraction. So from conservation of energy, the remaining energy, which is the kinetic energy, with which the electron will be liberated, is obtained from the basic conservation of energy, which is kinetic energy will be equal to hc by lambda minus phi. And the last important thing from our concept of photoelectric effect is, if the photons exhibit wave as well as particle nature, we know that particles will have a momentum associated with that, and that momentum is given by the de Broglie's formula, which is momentum is equal to h by lambda. And if we substitute the value of h by lambda from this equation, E energy is equal to hc by lambda, then this will equate to energy divided by the velocity of light. Now just to define what are these h, what is the numerical value of Planck's constant, what is the numerical value of the speed of light. We know these things, but just for a revision, the Planck's constant is 6.63 into 10 to the power minus 34 joules per joule second. Okay, so joule second which can be converted in terms of electron volt second, and electron volt is equal to H in terms of this unit electron volt second is 4.14 into 10 to the power minus 15. So in atomic physics or in modern physics, instead of using the SI unit, we many times for energy we many times use the unit of electron volt for energy. What is electron volt of energy? What is the unit? Electron volt, the unit is what is the energy which an electron will gain if it accelerates through a potential of 1 volt. If the potential difference between these 2 points is 1 volt and I release the electron, this will be attracted by this potential difference or repelled by the potential difference, depending on what is the sign of the potential difference. But the energy gained by this electron will be equal to E times V. Okay, correct. And if V is equal to 1, okay, so the definition of 1 EV or electron volt is the energy gained by an electron when it is accelerated through 1 volt. So energy of the electron when it is accelerated by 1 volt. But if volt is 1, potential difference is 1, then E will be equal to E. Correct? So what is the charge of an electron? It is 1.6 into 10 to the power minus 19 coulomb. So 1 joule, so if I equate this, so 1 joule will be equal to, or this is the electron volt. Okay, this is the unit of electron volt, EV. This will be in joules. So 1 electron volt, if I substitute the value of E here, is equal to 1.6 into 10 to the power minus 19 coulomb. So 1 electron volt will be in effect be equal to 1.6 into 10 to the power minus 19 joules. Okay, so if I substitute the value of electron volt, if I use this conversion factor, then 6.63 into 10 to the power minus 34 will come to be about 4.14 into 10 to the power minus 15 electron volt second. So it is important to learn both these constants both these values in terms of these constants, because it will be useful in solving numerical problems. And c is the velocity of light. C is the velocity of light in this formula, and it is equal to 3 into 10 to the power 8 meter per second. And we know from theory of relativity that whatever be the frame of reference, the speed of light is always constant. And another important constant in modern physics is the mass of an electron, which is equal to 9.1 into 10 to the power minus 31 kg. Okay. Also in last class we discussed that in Bohr's model, an electron can take only particular radiuses and particular energy levels. So each radius is corresponding to a particular energy level. So electron can take only those radius which satisfies this equation Rn is equal to n square by z, where n is the orbital number, n can be 1, 2, 3, n is the orbital number, divided by z. Z is the atomic number of the molecule. So for hydrogen it is 1, for helium it is 2, for lithium it is equal to 3. So Rn, the simplified equation is Rn is equal to n square by z, 5.3 into 10 to the power minus 11. And in the last class we had derived this. Okay, and energy in this orbital is given by minus z square by n square into 10 to the power into 13.6 electron volt. So here again we get the term electron volt here. So that's why it is important to know the definition of H in terms of electron volts also, because lot of formulas for sake of simplicity are written in terms of electron volts. So energy of an energy in the nth orbital, energy in the nth orbital is equal to z square, where z is again the atomic number of the atom, z square by n square, n is the orbital number, into 13.6 eV. It is useful to remember both these formulas because they will help to solve numerical problems easily and quickly. So apart from this, we also studied the hydrogen spectral series. We studied that when hydrogen is heated, it emits radiation, and that radiations are not continuous but they take discrete values. Okay, and this radiation is called Lyman series. This group is called Balmer series. This group is called Paschen series, and so on and so forth. And we studied that we can predict the wavelength, or these wavelengths are related by this formula 1 by lambda, where the lambda is the wavelength of the emitted radiation, is equal to the Rydberg's constant into 1 by n dash square minus 1 by n square. And our next objective is to again understand what is Lyman series, Balmer series, Paschen series, and derive the formula for the spectral lines. Okay, so conceptually again we will be using the conservation of energy. Okay, so we see here that there is a negative sign in the energy. The negative sign of an electron has negative energy because electrons and proton is attracting the electron. Okay, so it is assumed that at infinity the electron has at zero energy. Okay, and when I bring it towards the nucleus, it experiences an attractive force. Okay, so it has the power to do work. Okay, it can do work. Okay, so as I move it closer and closer, the energy of the electron, because it is a negative charge, what is the formula for energy? Energy is equal to k q1 q2 by r squared. Okay, so k energy is equal to k q1 q2 by r squared. So when it is at infinity, or it is at a large distance, it can do more work. Okay, why? Because this electron, because this nucleus is attracting this. Okay, so it can move from this point to this point. Okay, but when it is nearer, okay, then also it can do work. It can move from this point to this point, but now it can move to a lesser distance because it is already very closer to the nucleus. Okay, so that is the reason the farther the electron, the more the energy, the nearer the electron, the lesser the energy. Okay, so and because at infinity the energy of electron is assumed to be zero, that means as I bring it towards the nucleus, its energy decreases. That means its energy becomes negative. Also, it can be thought in another way. How does an electron fill up? Okay, so electrons always take we know electrons will take the nearest orbital first, then it will fill the second orbital, then it will fill the third orbital. Why it does that? We know that like a ball rolling. Okay, a ball will always take the lowest energy position first. Correct? So similarly, an electron will always take a lowest energy first. So that's why the first orbital has the lowest energy, second orbital has a higher energy, third orbital has a more high energy. Okay, so when I want to take when an electron jumps from say fourth stage to the first stage, what happens? Its energy decreases. Correct? Energy decreases when an electron jumps from fourth stage to the first stage. Okay, so where will that when electron jumps from fourth stage to first stage, its energy in the fourth stage will be given by minus 13.6 into z square divided by 4 square, and the energy in the first stage will be given by minus 13.6 into z square divided by 1 square. So its energy decreases. Where will this extra energy go? This extra energy will come out as a light energy. Okay, so it will release a photon, okay, whose energy is the difference between the, from conservation of energy. Again we are using the conservation of energy. So when an electron goes from fourth to first stage, first orbital, it will release an electron, it will release a photon of which will have the energy which is the difference in energy between the fourth orbital and the first orbital. Okay, so what is, so this has been represented by these lines. So n is equal to 1 has lowest energy level, n is equal to 2 has higher energy level, L is equal to 3 has more energy, n is equal to 4 has more energy, and so on and so forth. Okay, so whenever an electron jumps from second orbital to first orbital, a radiation will be, a light will be emitted. Similarly, whenever it will jump from third to first, then also one light will be radiated. Whenever it will jump from fourth to 1, similarly whenever there is a jump, okay, there an energy will be released. Okay, so let us take a general case. Okay, suppose suppose a particle, or sorry, an electron is jumping from mth stage to nth stage. Okay, then what will be the energy of the photon which is released? The energy of the photon which is released will be equal to the difference of the energy between mth and nth stage. Okay, correct. So the energy of the photon will be equal to the difference from the conservation of energy. Energy of the photon will be equal to the energy, the difference in energy of the mth minus En. So what is Em? Em is minus 13.6 into z square by m square. Okay, what is En? En is minus of minus, okay, minus of minus 13.6 z square by n square. Okay, so it is going from mth stage to nth stage. So if I just simplify this, it will be just 13.6 z square will be common. Okay, z square will be common into 1 by n square minus 1 by m square, which should be equal to energy of photon. And what is the energy of photon? We know energy of photon is E is equal to h, we just studied, again revived, hc by lambda. So this is the, this will be the energy of photon, this will be the energy of the photon which is released, and if I substitute the value of energy of photon, it will be hc by lambda. Okay, so what will be the wavelength? What will be the wavelength of light which will be released? So here, for 1 by lambda is equal to 13.6 divided by hc, okay, into z square 1 by n square minus 1 by m square. And suppose it is a hydrogen atom. If it is a hydrogen atom, then z is equal to 1, then this term will vanish, correct? So we will have 1 by lambda is equal to 13.6 divided by h into c. Now notice here that 13.6 is, this energy is in electron volt, correct? This energy is in electron volt. So the correct Planck constant to be used with this value would be 4.14 into 10 to the power minus 15 electron volt, not this. The value of Planck constant to be used should be the value, the corresponding unit should be consistent, correct? So because this energy is in electron volt, so the value of Planck constant to be used should also be in terms of electron volt in this formula. And obviously this is constant, H is constant and C is also constant, correct? So this term is a constant quantity, correct? So I can replace this as a constant R divided by 1 by n square minus 1 by m square. Oops. Okay. So basically what I have done, I have derived this Rydberg's formula from the basic energy conservation law. Okay. So now finally I have this formula 1 by lambda, the energy which is 1 by lambda is equal to R 1 by n square minus 1 by m square. Okay. So this series, okay, see here in this series all the photons are emitted because of a jump of electron from n is equal to 2 is equal to 1, or n is equal to 3 to n is equal to 1, or n is equal to 4 to n is equal to 1, or n is equal to, so here, okay, this series of photon is generated by jump of electron to n is equal to 1. Okay, so here n is equal to 1, m can be 1, 2, 3 or not 1, electron cannot jump from 1 to 1, then no energy will be. So here n is equal to 1, m can be 2, 3, 4, 2, 3, 4 and so on and so forth. So this series is what we get as a Lyman series, okay, where electron jumps from higher states to n is equal to the first orbital. Similarly this one, so let me write it in blue color. So this state, this series where n is equal to 2, okay, n will be equal to 2 and m will be equal to, it is jumping from the higher states, so 3, 4, 5, so m will be equal to 3, 4, 5, okay. So this is what is the Balmer series. So Balmer series is obtained when an electron jumps from higher states to the second orbital, okay. Similarly this one is called the Paschen series. So Paschen series is obtained when n is equal to 3 and m will be equal to 4, 5, 6, etc. Correct? So Paschen series is obtained when the electron jumps to the third orbital from the higher orbitals. So when electron jumps from higher orbitals to third orbital, Paschen series is obtained. Okay. So this completes our discussions on photoelectric effect and Bohr's model. In the next video, we will discuss a few things about another interesting topic, which is X-rays. So see you in next video.